So let's look at the general issue first. So we look at the data and signal. Well, data is the content, and signal is the form. Okay, so you have the data, and in what form you are going to represent the data and transmit the data. Okay, that's the signal. And it could be analog or digital. So what is analog data and digital data, respectively? Okay, what is analog data? Your voice, your image, the music itself, they are analog data in nature. In their nature, they are analog. Your voice and your image. And then if it's analog data, then how can I store the analog data in a computer? Then I would need to transform the analog data into digital data, okay, into the digital form. Then I would need to do the sampling. Usually you would require sampling. So my voice, usually a human voice has a frequency bandwidth of 3,000 hertz. 3,000 hertz. So then, well, the music will be higher. Well, the music would have a wider bandwidth because the quality is better than the human voice. Okay, and if I want to transform my analog voice into digital form, then what I should do is to do the sampling. I need to sample the voice, and because the voice is has a bandwidth of 3,000 hertz, 3K hertz, and there's a theorem, the Nyquist theorem, the Nyquist sampling theorem that we will see next. It tells us that in order to sample an analog source with a certain bandwidth, your sampling rate, in order to capture the analog data accurately and also recover it completely later on, you need to have a sampling rate which is doubled the bandwidth. So if the bandwidth is 3,000 hertz, it means that the sampling rate needs to be 6,000 samples per second. So 6,000 per second. Well, however, some people have a bandwidth larger than 3,000. So, say like 4,000. See, some people have a higher frequency in their voice, or lower frequency in their voice, higher frequency component or low frequency component in their voice. Then their bandwidth will be wider, like 4,000 hertz. Then, according to Nyquist theorem, the sampling rate needs to be 8,000 samples per second in order to accurately capture the data, the analog data. So you do sampling, and 8,000 samples per second means how many samples? How many seconds per sample? How many seconds per sample? That'll be 1 over 8,000, right? And 1 over 8,000 seconds will be equal to 125 microseconds. So every 125 microseconds, you need to sample once. Okay, so you need to do the sample, and each sample will be, say, like 8-bit. If each sample is 8-bit, then every 125 microseconds, you got a sample of 8-bit to capture the voice. Then how many bits per second totally? That'll be 8-bit multiplied by 8,000, right? Because every second you have to sample 8,000 times. So you got 8 multiplied by 8,000. That'll be 64K bit per second. So the voice. So if the voice is sampled directly, then into the digital form in binary, and then you transmit the voice, the digital voice. Then it'll be 64 kbit per second, right? And that's uncompressed. However, you can compress the voice because well, there's some compression technique that you can compress the 64 kbit per second into something like 8 kbit per second, or even 6 kbit per second, or even 4 kbit per second, in order to carry more phone call in a digital link. So that's sampling. So if it's original, it's analog source, the voice, but now I digitize, I do the sampling and I digitize this voice, and then I do some compression so that I can compress the bit rate into from 64 kbit per second to like 8 kbit per second. So that's from analog data into digital waveform and digital form, and then if I transmit the bit stream in binary in digital form, then I'm doing, and this will be digital signal get transmitted, right? If I transmit the bit stream with, say, some simple coding. Now, we will talk about coding in section 2.3. So you do coding and then transmit a bit stream, or you do coding and then next you do modulation. Okay, and so you see that we can the data is original analog and then transform into digital signal. How about digital data originally? What is the data which is originally digital? That's your computer files. They are originally digital there. So it's digital data. And if you want to transmit it, you can do a coding and then do modulation and then transmit it. So that's digital data. How about digital signal or digital analog signal? If it's transmitted in a digital signal, or you just do coding and then transmit it, then it's a digital signal in transit. However, if you do coding and then do modulation, then you are transforming the digital signal into the analog signal and then transmit it. Okay, then it becomes analog signal. But however, some people, many textbooks still view that kind of signal as digital signal, although it has the analog waveform, because the things embedded, I mean, digital signal embedded in that analog signal is actually digital. It was digital, but has been modulated into analog signal, analog waveform. Then some textbooks still say this is digital signal, although it has the waveform of analog waveform. I know this might confuse many of you, but I would say that the text has some explanation on this, and I would say that that kind of analog signal has certain format. It's not a random analog signal. It has certain format, and it's modulated by the format depends on the modulation scheme, and it has certain format. It's not a random analog signal. It's different from a random analog signal source. Okay. Though the signal format is analog, okay, we could still say that it's still digital signal, but in an analog format. Okay. We'll see that. We'll see that again in one of the slides next. Okay, and we will see also the transmission flow and reception flow. The flow that you need to go through for the data to become the signal, transmitted signal, or vice versa. And as I said, for the transmission, you probably would need to do coding, and perhaps you also need to do modulation. And as I said, for modulation, it usually means that you want to go through the vulnerable air interface, or you want to traverse far, very far in a wire line. Then you do need to do modulation. And that's called digital modulation. You transform the digital signal into analog format. Okay. Okay, and there are some impairments that we will see, that noise, interference, and distortion. These are the impairments. So these are the general issues we look at. And see, we can see that here's a summary of what I just said. I said the data could be digital or analog. Digital data means it's a discrete value of data for storage or communications. For analog data, it's continuous value of data, such as sound or image. So the data, in its nature, is analog. And the signal could be analog signal or digital signal, where the digital signal is a discrete time signal containing digital information, while the analog signal means the continuous time signal, not discrete time, continuous time signal containing the analog information. And here the definition of digital signal is kind of the analog signal, the definition here is kind of rigid. What if I have a signal which is analog, but the data, the information there is digital? It's digital. Then I would say that that's digital signal, according to this definition. If I have digital data, digital information, but in analog signal, analog format, continuous signal format, then I would call it digital signal, which is, even though the signal format, the waveform is sine wave, we still call it digital signal, according to this definition. And that's many books adopt this kind of definition, even though the waveform is analog. Okay. However, sometimes we want to relax that definition, saying, okay, we probably would say that it's analog signal because it's in analog format. But that kind of analog signal has certain format. It's depending on the modulation scheme. Okay. Okay, and we'll see the signal. Well, next, if you are not EE background, then the following discussion might confuse you further. So, but try to comprehend as much as you could. Okay, so we talk about the analog data and signal, and could be analog or digital. Next, we add another ingredient, which is the periodic and aperiodic. Periodic and aperiodic. Here we got periodic, and it's analog. Periodic analog signal. Spectrum in the frequency domain will be discrete. What does that mean? See, I have a sine wave with a frequency of 100k hertz, and another sine wave, this sine wave with a higher frequency at 400k hertz. So I got two sine waves. And they are periodical. And for this sine wave, the 100k hertz, if I view it in the, if I view this sine wave in the frequency spectrum, the x-axis is the frequency and y is amplitude, then you will see a discrete energy. We don't have energy out at other frequency, but only free energy at this frequency. Okay, and for the other sine wave, we have energy. Energy means amplitude. Okay, we have energy at this frequency, and the energy is higher because the amplitude is higher here. The amplitude is high, of this is higher than this, so we got more amplitude at this frequency, and we got no amplitude or no energy at the other frequencies. Okay, so we call this discrete, and because it's periodical, the sine wave is periodical, so the energy, I mean the in the frequency domain, is discrete. So we say that the spectrum is discrete. However, if we look at the other analog signal, this is a periodical. This is not a sine wave. Not a sine wave. It's a periodical. It looks quite random. And then if we draw this, because their frequency, there'll be many frequency in terms of the spectrum. So we have energy at different frequency, and then there's a frequency bound, say F1 and F2. And within this, we got energy everywhere. We got amplitude everywhere. So then the spectrum is what? Continuous. So we got continuous spectrum for this analog, a periodic analog signal. Okay. How about digital? If this is a digital signal and a periodical, and this is a periodical. So we got periodic digital signal and also a periodic digital signal. Then here, there's a theorem called Fourier theorem. Fourier theorem tells us that you can transform the square wave, the periodical square wave, into discrete amplitude, discrete energies, at discrete, at discrete frequency domain. So we would have energy at a certain frequency domain, and it's a multiplicative of the base frequency. If this is a base frequency, and you would have 2f, 3f, you would have energy there, and the energy or the amplitude at the base frequency will be the highest, and it decrease, okay, and eventually vanish. And if you add up this together, the Fourier theorem says that it would reconstruct the periodical digital signal. The periodic digital signal will be reconstructed. That's the Fourier theorem. If you take the engineering mathematics, Fourier theorem is the one of the most important theorem covered there. So the periodic digital signal is actually, if you look at into the frequency domain in the spectrum, then you will see that you have energy only at discrete frequencies. So it's a discrete spectrum. However, if it's a periodic digital signal, you don't have that features. You don't have that features. Beautiful as beautiful as described in the Fourier theorem, then you would have energy everywhere, not at discrete frequency. You would have energy at a continuous frequency domain. Okay. So the spectrum will then become continuous, just like a periodic analog signal, where the frequency domain is what? I mean, the frequency spectrum in the spectrum in the frequency domain will be continuous. So this will be the same. So we have a conclusion that if it's whether it's analog or digital, fine. If it's periodical, then the spectrum will be discrete, right? If it's aperiodical, then the spectrum will be continuous. Okay, whether it's analog or digital. Okay. Okay, now so now we got the idea of digital data and signal, right? Data versus signal, and digital versus analog, discrete versus continuous, and now we got periodical versus aperiodical. So please, think it over and try to see their possible combinations. There's a sidebar principle in action. Tell us the Nyquist theorem and the Shannon theorem. It says that the Nyquist theorem has two theorems. It says two things. One is the sampling theorem. It says that we just mentioned that if the source has a frequency of f max, say 4,000 hertz, then in order to sample the source, the analog source, correctly and completely, the sampling rate needs to be doubled the frequency of the source. So if it's 4,000 hertz, then the sampling rate should be 8,000 samples per second. That's the first sampling theorem. And another thing it says that is the maximum data rate for a noiseless channel, meaning if the channel is clean, no noise, then what is the data rate, maximum data rate? It says that it will be 2 multiplied by bandwidth multiplied by log 2L. The L here is the number of states to represent a symbol. So usually the basic one will be 2, meaning that I would just use two possible states to represent a symbol or a signal symbol. Then I would not gain anything. However, if my number of states or number of levels could be, say, 256, for example, then log 256 will become 8, right? Then my bit rate, maximum bit rate will become 6 multiplied by 8. That'll be 48 kbit per second. So in a noiseless channel, the maximum bit rate highly depends on this value, L. If L is the primitive one, that is 2, then the maximum data rate will be 2 multiplied by the bandwidth. 2 multiplied by the bandwidth. So actually, if you take this out, then this 2b is the same as this. That'll be the bandwidth multiplied by 2 will be the bit rate. However, you can gain more bit rate by having more state to to represent a symbol. Okay. That's the Nyquist theme. But then the channel will not be clean, will not be noisy. It is noisy. So we need another formula to calculate the maximum bit rate for noisy channel. And the Shannon theorem says that, okay, the bit rate, the maximum bit rate should depend on what? The signal to noise ratio. So it has a formula of this, B, the bandwidth multiplied by log 2 multiplied by 1 plus S over N. S is the signal, N is the noise, which is called the signal to noise ratio. And in this example, I'm putting the example here. In this example, the signal to noise ratio is 1,000. Then you got a bit rate of 32.9 kb per second. So it says that the bit rate, the maximum bit rate for noisy channel would not depend on the number of states. It would depend on the signal to noise ratio. And in the example we put here, you will see that, okay, I have for the 3K hertz channel, the bandwidth of 3K, and the maximum data rate for noiseless channel is, in this example, is 6K, which is lower than the noisy channel. So you would wonder why, and the reason is because the noise for the noiseless channel, you didn't put it to the extreme. If you have much larger L, say if you have large number L, then the bit rate here could be larger than this. So it's possible, depending on your coding scheme. Here, the coding scheme. Depending on your coding scheme and modulation scheme, you could have a bit rate larger than, for noisy channel, larger than the noisy channel. But for that noise channel to reach that bit rate, you need to have, again, quite sophisticated coding and modulation scheme. Otherwise, you wouldn't be able to reach that. And that would only tell you the bound. So the Shannon result is sometimes called the Shannon limit. It's the upper bound. And don't expect that the coding and modulation scheme that we use daily would reach that kind of limit easily. That limit cannot be reached easily. It's difficult to reach the limit. It's the ceiling. It's the ceiling. It doesn't mean you can reach the ceiling easily. Okay, the flows, the transmission and reception flow. And this figure you can see from on the left-hand side, you have source and sink. So the transmitter is here, and the receiver is here. So the transmitter transmits, well, it got transmitted here, and through the channel. And the channel could be wired on a wire link or wireless link, and then reach the receiver. And between the source and the transmit, there'll be a series of components. So you would do coding, which is called, you do coding here. This is source coding and channel coding. And then do line coding, and then do modulation, and then transmit. And you might have multiplexing in the middle. And multiplexing could be put here or here. Put here or here. depending on how you do the multiplexing. In this figure, we put it here, and usually it means that multiplexing scheme is TDM based or CDM, time division based or code division based. But if it's frequency division multiplexing, it will be put here. It will be put here. And I explained it in the text in the book. And so sometimes it's put here, sometimes here, depending on how you do the multiplexing. And we have explained the coding, the line coding and modulation. This is to transform a digital waveform to another digital waveform that has better quality or better property. We will explain later what it does. And this will transform the digital waveform into the analog waveform that is easier to transmit, to get transmitted in the wireless link or long distance link. Okay. How about this? We haven't seen this. We haven't discussed this, the source coding and channel coding. The source coding is to, remember I said that you would sample the voice and then you got 64 kb per second, right? And then you do the compression to reduce the bit rate to 8 kb per second. That kind of compression is called source coding. Source coding. How about channel coding? After I do the compression and before I pass through the line coding, I might want to do channel coding to make to do error control. Usually I do error control, say if it's if I add error correction code or error detection code. So that if I put error detection code, meaning that the receiver, after receiving the bit stream, it will be able to tell whether the bit stream has an error there. Or if I put error correction, that means the receiver, after receiving the bit stream, could detect whether there's an error. If there's an error, the receiver will be able to correct the error there. And that kind of error detection or correction is called channel coding, the channel coding. So the source coding is about the compression, mostly about the compression, and the channel coding is about the error detection and correction that you want to do at a physical layer. Okay, we will talk about error detection and correction in almost every chapter. However, in the physical layer, we could do error detection and correction at a physical layer too. Not just at the upper layer, we can do that at a physical layer. And this is called channel coding. Okay, so you would have this. Well, perhaps you only have source coding but not channel coding. Perhaps you have both. And then if it's time division multiplexing or code division multiplexing, you would do it here. You mix with other source. You mix with other source. If it's still in the bit stream, the digital bit stream, then you do it here. If it's not in the bit stream, it's frequency, another frequency, you do it here. You do it here, another frequency. So if it's FDM, if the multiplexing scheme is FDM, then you put it here. This box will be put here. Okay, and then you do line coding, transforming the digital signal into another form, and then do modulation into the analog format. And for the reception, it's the other way around. You do the demodulation, you do the line decoding, demultiplexing, and then also decoding here, and then back to the original the information sync. Say if this is a voice, so this figure will be more meaningful if you think this is someone you are talking here. It's your voice, analog signal, your voice here, and it's your friend's ear. It's the ear that listens to your voice. So you would need to play back the voice, right? So that your voice will be played back here, so that your friend can hear it. So your friend's ear is the sink. Okay, I have mentioned the baseband versus broadband, where the baseband transmission means it's in the original digital format, no modulation, without modulation. But broadband transmission means that you do modulation because you want to transform into the analog format so that you can traverse far or traverse through the air interface. So sometimes people say, okay, broadband means the bandwidth is large, and baseband or narrowband means the bandwidth is small. It's not correct. It's a misunderstanding. But it's true that broadband transmission usually has transmit on a link with abundant bandwidth. That you would do you would transform the signal to an analog format within the carrier frequency. Say I want to put it into this carrier frequency, and I have other frequency for other source, for other traffic source. So I would have many traffic multiplexed. Many traffic sources multiplexed together on one link. Okay, so then it's really the bandwidth is large, in order so that it can accommodate so many traffic sources together. But by definition, broadband transmission means that you do modulation. And so before we end, I'd like to talk about the, let me finish by 3 more slides. The line coding. Why do we need, okay, it's a digital format, and I put it into another digital format. What's the deal? Why do I need to do this? Because I'm transforming a digital format that is not good for transmission. I transform it to another format which is better for transmission. So let me, so if this, well, let's preview a slide here. That if the original signal is this is original waveform. Yeah, okay. If this is original waveform, then I might transform it into different formats. And these schemes have different properties. Some of them are better in certain aspects. Okay, so why am I doing this? Okay, the reason is because if you transmit a square wave 0, 1, 0, 1, and if you happen to say, if you encode it straightforward, say 1, 0 means 0 voltage, 1 means voltage at 1, a signal with the voltage of 1. If you transmit bit 0 and 1, then it will be 0 and then 1, the voltage 1. And then what's the problem with this kind of straightforward scheme, straightforward coding scheme? What happens if we have continuous bit stream of 0, say 0, 0, 0, 0, 0? Then your signal will be flat for many bit time, right? It will be flat. Then what problem with this? The receiver clock will lose synchronization with the transmitter clock. So I have a transmitter running at a clock rate of say 64K hertz, for example, or 1 megahertz. Say usually say 1 megahertz. My clock rate is 1 gigahertz, for example. My clock rate. And the receiver clock rate is also 1 gigahertz, supposed to be. But sometimes they will shift a little bit. So if I have a bit stream of 0 continuously for say 5-bit time, then the receiver would have difficulty to know, okay, is this a 5 consecutive bits of 0 or 4 consecutive bits of 0? The receiver have difficulty to tell that, because it's not easy to tell whether this is continuous 4. So the receiver needs what? Needs to have some signal change. There should be some signal change in the middle in order to synchronize the receiver clock. So we need to calibrate the receiver clock for synchronization bit intervals to the transmitter's clock. So their clock needs to be synchronized, otherwise they would have difficulty. The receiver would have difficulty to tell. And another problem will be the receiver would have the starting time. The starting time might have a shift. See, I start here. I started at this point, but the receiver might start later a little bit. So there will be a shift, and we call it baseline wandering or drift. So if this is there's some loss of if this synchronization issue is about time interval, and this will be about time starting point of the time, of a bit time. So this will be interval, and this will be the starting point. So they have shift in the interval or in the starting point, then they both will create problem to the receiver in recognizing the digital value, the digital signal value. Another problem will be the DC component. See, in the straightforward scheme saying if it's 0, then I send voltage 0. The signal voltage will be 0. If it's 1, the signal voltage will be 1. Then you would always have positive voltage, right? On the average, you will be positive voltage. It's like you take the swing, 荡秋千, swing, and you always swing forward. You don't swing backward. And what happened? It will consume you a lot of energy by doing that. So you need to do what? You need to swing positive and negative, right? You don't swing this positive and then stop here, and then swing positive and stop here. You don't. You swing positive and then negative. That will save you energy, right? If you swing just positive, then that will be too energy consuming. So DC voltage means that you have a DC bias. It's a non-zero component around 0 Hertz, and it will consume more power. So you don't want DC voltage. So what happened? What will be the better scheme will be, you should go to -1 voltage if it's 0, and +1 voltage if it's 1. So then you will swing positive and negative, and then on the average the power, I mean the voltage will be what? 0. Will be 0. Then that will consume much less energy. So that's the DC component or DC bias problem. So considering this, then you will be able to tell which scheme will be better. So we will see that next week, and by having those concepts in mind, you would tell which scheme will be better. And then the modulation. I think I'll need to stop here because I'm 10 minutes over the time. So let me stop right here. Any questions? Okay, remember that next week you need to turn in homework number 1 and don't be late. And if you have questions, post it on the Facebook. And don't email me, because I would ask you to post on the Facebook. Because the reason is because I want to cook. I want to cook the Facebook community to make it with a lot of discussions. And your question will be answered within 1 day. So you don't expect that you post and you get it in 1 hour. It'll be 1 day. So post your question earlier. And if you post question, I would, on the homework question, I or TA would not be able to give you the answer directly, but we will try to give you instruction or hint, but not the answers. Okay, that's it for today. Thank you.